Let's talk about pedigrees. So, what are pedigrees? Well, pedigrees are illustrations of family history. So, we can define them as visual representations of a family's history. And this means that we can see how a certain trait or disease can be passed down through the family. Here, I'm just going to draw a pedigree so that we can analyze the different parts. In a pedigree, a circle indicates that it's a female, a square indicates that the individual is a male, a vertical line connects parents to children, a horizontal line indicates marriage between a male and a female, a circle or square that is unshaded indicates that that individual is unaffected. But a square or circle that is shaded indicates that that person is affected. And there are 4 modes of inheritance that can be illustrated through pedigrees. There is autosomal dominant and autosomal recessive, sex-linked dominant, and sex-linked recessive. So let's take a look at an example. Huntington's disease is an autosomal dominant trait. So let's indicate all the genotypes of all the individuals in the pedigree shown. So I'm going to draw out a pedigree. So this is our final pedigree. And remember that the question told us that this is an autosomal dominant trait. That means that all affected individuals, which means that people that are shaded in, must have at least one dominant allele. This is because if they show the trait, they have to have at least one dominant allele. So let's start out by writing one dominant allele for all individuals that are shaded. Once we've done that, we also know that all unaffected individuals must be homozygous recessive. And this is because if they had even one dominant allele, then they would show the trait. So if they had even one big D allele, then they would show the trait. But if they don't show the trait, then they have to be homozygous recessive. So now we can fill in all the unshaded individuals with a homozygous recessive genotype. So here I'm just filling in little d for all unaffected, uncolored individuals. Now we filled in the genotypes of most individuals, but let's take a look at the ones that we haven't. Now, if we look at this mother, she must have given a little d to this son because her son is homozygous recessive, and so is her daughter. That means that the father contributed one little d, but the mother must also have contributed the other little d for the child to be homozygous recessive. Therefore, we know that the mother in the first generation is heterozygous. Let's now look at this female daughter. We know that she has a big D that she must have received from her mother, because her mother is the only one that is affected. And since her father only has little d alleles, she must have received that from her father. Therefore, she is also heterozygous. And if we take a look at this son who has a big D allele that he must have received from his mother because his mother's the only one who is affected, his father must have contributed the little d allele because that's the only allele that the father has. So the son is also heterozygous. And we can fill in the same genotype for the other individuals in that generation. Now let's look at the third generation, where we have two offspring that are colored or shaded in, but we don't know which parent they received that big D allele from because both parents are shaded in. So the mother could have contributed the big D or the father. This means that we can't be sure of what the second allele of those individuals are, so we'll just leave a blank. And we filled in the pedigree. Now let's take a look at another example of a different mode of inheritance. Cystic fibrosis is an autosomal recessive disease. So let's indicate all the genotypes of all individuals in the pedigree. Here I'm going to draw out the pedigree. And remember that the question told us that this is an autosomal recessive disease, which means that all affected individuals or individuals that are colored in must be homozygous recessive if they show the trait. As a result, we can go ahead and fill in all the colored or shaded individuals with the little r genotype. The next thing that we can conclude is that all unaffected or unshaded individuals must have at least one dominant allele. So we can go ahead and fill in one dominant allele for all individuals that are not shaded in because they don't show the trait. Now, parents that don't show the trait must be heterozygous if they have affected kids. So parents of affected kids must be heterozygous. So let's take a look at the first generation. We see that these parents have an affected child. That means that both parents must have contributed a little r allele in order for the child to be homozygous recessive. Therefore, both parents must have the little r allele, so both parents are heterozygous. Similarly, in the second generation, since the father is homozygous recessive, he will contribute one little r allele, but the mother is unaffected. she does not show the trait. So we stated that parents of affected kids must be heterozygous if they don't show the trait. Therefore, since this daughter has one little r from her father, she must have gotten the other little r from her mother, and so her mother is heterozygous. We can use the same reasoning for this son. This son is homozygous recessive, so he must have received one little r from his mother and one little r from his father. But what about this individual over here? He is not married and does not have kids, so we don't know the genotypes of his wife or his kids. Therefore, we cannot be sure about what his second allele is. Let's do another example. Hemophilia is an X-linked recessive trait. Again, let's indicate the genotype of all individuals in the pedigree. So here I'm going to draw out our pedigree. Now recall that the question told us that this is an X-linked recessive trait. X-linked means that the trait or the disease is carried on the X chromosome. And the reason that this is important because it means that males need only one X with the little r allele in order to be affected, whereas females need two of the recessive X chromosomes in order to be affected. And recall that the reason is because females have two X chromosomes, whereas males have one X and one Y. So let's try to fill this pedigree out. The first thing I like to do is fill in all the individuals with whether they are a male or a female. So whether they have two X chromosomes or one X and one Y. Now, once we've done that, we can start out with the first individual. So this female is not shaded, which means that she doesn't have the trait. Therefore, she must have at least one dominant allele. This male is shaded in, so he is affected and must have a little r allele. We can keep doing this for all the other individuals. So this female is affected and therefore must have two r alleles. This male is unaffected, so his X chromosome must have the dominant allele. This male is affected, so he must have the recessive allele because this is an X-linked recessive trait. And this female is not affected because she's not colored in, and therefore she must have a dominant R allele. These three males must have the X chromosome with a recessive allele because they show the trait. And finally, this female must have at least one dominant allele. So we filled out most of these, but notice how we don't have the second alleles of these three females. Let's start with the first one. So we can see that in the second generation, this female is affected. She has two recessive alleles. She must have received one from her father, and the other one must have come from the mother. Therefore, the mother in the first generation must be heterozygous. Now let's look at this female in the third generation. We don't know her second allele, but we know that she must have received the dominant allele from her father because her father's the only one that has the dominant allele. The mother is homozygous recessive. She has two X little r's. Therefore, she must have contributed an X little r allele because those are the only gametes that she can produce. And the same thing goes for this female on the right. The father contributed the dominant R, but the mother only has two little r alleles to contribute. Therefore, the mother must have contributed the X chromosome with the little r allele. Now take note of some key ideas about X-linked recessive traits. For X-linked recessive traits, more males tend to be affected than females. And we can see this in our pedigree because there are more males shaded in than females. In fact, if we count it, we have 1 male here, 2, 3, 4, and 5 males that are affected. But we only have 1 female that is colored in. So clearly more males were affected than females. Alright, let's look at one final example. Goltz syndrome is an X-linked dominant trait. Let's indicate the genotypes of all individuals in the pedigree. So here I'm going to draw out our pedigree. Now remember that this is an X-linked dominant trait. And also remember that females have 2 X chromosomes, whereas males have 1 X and 1 Y. This means that females and males need only 1 dominant X chromosome in order to be affected and show the trait. And for the same reason, unaffected females that are not shaded in must be homozygous recessive, because if they don't show the trait, they don't have any dominant alleles. And males that do not show the trait must have a recessive allele on the X chromosome that they inherit from their mother. So remember, females and males need only 1 dominant X chromosome to be affected. So let's look at our pedigree. All individuals that are shaded in must have a dominant allele. But the first thing I like to do is fill in all individuals with whether they are a male with 1 X and 1 Y chromosome or a female with 2 X chromosomes. Now looking at the first generation, we can see that the mother is colored in. Therefore, she does exhibit the trait and has 1 big dominant allele. We're going to use big T and little t. The father is not affected, so he has a little t allele. In the second generation, this female is not affected. Therefore, she has 2 recessive chromosomes. This male does show the trait, so he has 1 dominant allele. In the third generation, this male is not shaded in, so he's unaffected and has a little t allele. The same goes for this male over here, who is also not shaded in, so he also has a little t allele. But all 4 females in the third generation are shaded in, which means all of them have at least 1 big T allele. But what are the second alleles of these 4 females? Well, if we look at their parents, we can see that all females must have received the big T allele from their father, because their father is the only one who is affected out of their parents. Their mother has two little t alleles. Therefore, the only gametes that the mother will produce are X little t. So those are the only alleles that she can contribute. All 4 females will receive the X little t allele from their mother. And now we've finished the pedigree. But here are some key ideas. If a father is affected or is colored in and shows the trait for an X-linked dominant trait, then that means that all daughters must be affected. So all daughters have a 100% chance of being affected. And the reason is because all daughters receive an X chromosome from their father. So if their father has the dominant trait, then all daughters will receive that dominant allele. Also notice that here this mother has 2 little t alleles. So those are the only alleles that she can contribute to her sons. Therefore, if a mother is unaffected by an X-linked dominant trait, then all sons will be unaffected because sons receive their X chromosome from their mother.